Fourier talks, I would like to again remind everyone about the book stand organized by Hilbert in the lounge room. And as I said, they support us, and I hope that we can support them. And also, I would like to mention one more time that we will have an open postdoctoral position in the fall at the Nobel Junior Center. So if someone is interested in working with us, please let us know. And now, I would like to present to you the first annual, I can say that, Nobel Junior lecture at the February Fourier talks given by Professor Robert Fefferman. I don't know if Professor Fefferman brags about it, but we always mention that he studies mathematics here. And he will talk about some classical and open problems in harmonic analysis. Thank you.
Well, thank you very much for having me. Indeed, I certainly did study here, and any success I may have had, I think, is largely due to the excellent background I got here. And in fact, my first slide, which is sort of going to set the tone for this basic talk, very elementary. I learned this here, and I think part of this talk I'm going to try to convince a lot of my professors that I actually have mastered finally. So, you know, here all of us know, we teach and so on, you take a continuous function and you write out the integral and you try to differentiate it and get back to the original function. I think that's supposed to be the punchline. And, you know, in a way, I mean, with hats off to Newton and Leibniz and all this, very deep and wonderful thing, still, you know, when you write it out, basically what it says is that if you have a continuous function and you average it on a very small interval, where it's roughly constant, you know, the average is essentially that constant. So that's, in a way, I think it's fair to say somewhat obvious, right? You're averaging roughly constant function, you get that constant. But when you go to the Lebesgue integral, I still find it quite fascinating. You know, you have an integrable function on Euclidean space, and you take, let's say, it doesn't have to be a ball centered, doesn't have to be centered at the point, but let's just say you have a ball of radius r centered at the point, and you average the function over the ball, you shrink the ball around the center point, and the averages converge to the function almost everywhere, except on the set of n or 0. And I think I learned that here as well. But that's just not obvious, at least not obvious to me, because the function is probably discontinuous everywhere, it's not roughly constant, and so on. Well, the moral of the story is I did learn here that, you know, an L1 function, the continuous functions of compact support are dense in the L1 metric. And so, you know, morally, the continuous functions sort of predominate. So, okay, so presumably there must be some way of passing from a continuous function, a nice function, to the average ordinary L1 function, and so morally, maybe that's why this is true. But when you really try to write down a proof, it involves a fantastically gutsy idea, I would say, the way to describe it, of Hardy-Littlewood. And you know, those of us in the field, you know, many of you have seen this, you know, hundreds of thousands of times. Those who aren't might be surprised, and you know, again, we've seen this so many times, those of us in the field, you know, you lose the surprise after the 5,000th time you look at the operator, but you know, when it has to relive the first time you see this, the idea of taking the function, let's take its absolute value, you know, we don't worry about cancellation here, so we have a positive function, the absolute value of f. Instead of taking the limit of the averages, which I guess the fundamental theorem says converges almost everywhere to f of x, Hardy and Littlewood dared to take the biggest of all of the averages and assign that value to the point x. So you take a point x, take all balls, let's say centered at x, of any size whatsoever, take all the averages in question, and take the maximum, soup of all of them. And that's called the maximal function, for obvious reasons, the maximal function, the Hardy-Littlewood maximal function of f at x. And not only, so, you know, I think naively that could be infinite everywhere. I mean, it's such a remarkable construction, taking the biggest of all these things instead of the limit, but actually not only is it not infinite everywhere, it's finite almost everywhere, and in fact it's very well behaved. If you haven't seen it, for the algebraists, geometers, number theorists, I mean, if f is an LP function, then m of f, the maximal function, is also an LP, and in fact the sizes are essentially comparable. You know, modulo some constant depending only on p. When p is greater than 1, this is an important theme, not equal to 1, greater than 1. When p equal 1, for certain reasons that we'll get to, this is not a bounded operator. You know, if f is an L1, m of f is not an L1. On the other hand, it is true, we call this in the trade a weak type inequality, and what it means is if f in L1 is normalized to have size 1, and you compute the maximal function, You can't say it's an L1, but you can say that the measure, the Lebesgue measure of the set where it's tremendous, let's say alpha is 10 to the 10 to the 10, where m of f is tremendous is very small. So imagine the L1 norm of f is 1, normalize that 1, the size of f is 1. The measure of the set where m of f is tremendous is like 1 over alpha, very, very small. So at least, morally speaking, if not bounded, you know, you have an input which is decent, size 1. The output cannot be enormous on a huge set. It's got to be very enormous on a tiny set. So that's weak type. And now, you know, I think this is very appropriate. Norbert Wiener, here he is, generalized this to n dimensions, and he proved that given, well, first of all, he proved this estimate, weak type estimate, and the boundness of LP, and also this explains very nicely that moral principle that you can differentiate the integral. The fundamental theorem of calculus or Lebesgue, even though the functions you're averaging over small balls are not continuous anywhere, it explains very well why you can pass from the moral principle of the density of continuous functions in L1 to the average ordinary L1 function, which presumably looks ugly. And the answer is, well, you take your L1 function, arbitrary L1 function, pretty ugly looking. You write it as a continuous function, which, and again, they're dense, so, you know, C can approximate F in the L1 sense very well. The error F minus C then is really tiny in the L1 norm. If AR of F denotes the average over a ball of radius R, centered at X, this is a linear process. And now we watch as R tends to 0, and we ask, does that converge as R tends to 0? Well, this part does converge because C is continuous. So the averages, for the same reason as you know, what I learned here as a freshman, this will converge to the value of the function everywhere. And then what about this? Well, how much oscillation, the lim sup minus the lim f, if this is not going to converge, let's see by how much it misses quantitatively converging. The place where this creates a problem for us, where the lim sup and lim inf are not the same and are bigger than some fixed quantity, is bounded, well, by twice the supremum, where twice the supremum is bigger than that quantity. In other words, if the function, if AR, these averages of F minus E, stay pathetically small all the time, you can't have oscillation. A tiny, tiny quantity can't oscillate by more than lim sup minus lim in. It can't be more than twice the biggest the absolute value of the quantity can be, if it's trivial. Well, is this trivial? Yeah, it is, because F minus C is a tiny, tiny function, and AR of F are simultaneously controlled by M, by definition. M is exactly the thing that controls all of the AR simultaneously. Supremum of all of them. So you have a small input, an operator, well, in L1 it's not bounded, but it's what's called weak type, and that means everything is small. If this function is as small as you wish, this is nice, M is a nice operator, takes this small input, gives you a nice small output, not in the L1 sense, but it's weak type, it's fine. So that's what you need for the Lebesgue. That explains Lebesgue. But the maximal operator, and I'm going to try to propagate, it's no secret, I'm propagandizing here for the importance of maximal. I think it's fair to say, although I'm no historian of mathematics to say the least, I think it's fair to say that maybe even Hardy and Littlewood did not realize how fundamentally important maximal functions were. In fact, I think it's kind of clear because I'm going to talk about objects called singular integrals. I'm not sure they knew about, you know, all the theory of singular integrals, and maximal functions control them. So, I mean, how could they have? But anyway, okay, so you have a Fourier series. You have a function that you want to take the Fourier, I'm sorry, I sort of skipped over, I passed over. Here's another application of maximal function. You take an integrable function and you write out a Fourier series. You try to write it as a bunch of sines and cosines or exponentials. So these are what are called the Fourier coefficients to the non-analysts in the audience who have not, do not dream about this every day and night. So the question is, does this converge? And does it converge to the function? And it's a very deep and very, I mean, Fourier just announced, I think, or just thought that, you know, didn't know what a function was, didn't even know the formal definition of a function. So Fourier series converged to represent the function. And then the question, you know, for the next several hundred years, does it really, is this really true? And there's all, one could have, you know, hours and hours on this and courses devoted to whether or not these things converge. And of course, there are great experts in the audience who know all about this and do dream about it all day and night. The partial sums It turns out the partial sums are not necessarily quite as good as you'd like them to be. We'll get to that in a second. But if you average the partial sums, these are called the Cesaro means. So instead of looking at the partial sums, you list them out. You take the first, well, I guess you're starting with the 0th one, so there'd be, instead of capital N, there'd be N plus 1 of them. You average them. And you call those sigma N. They are dominated pointwise, literally, essentially, there's a constant, but by the maximal operation, by the maximal function of F. And in particular, the same exact argument as proves the fundamental theorem of calculus proves that if F is in L1, the Fourier process works, in the sense that the Cesaro means, maybe not the partial sums themselves, but if you average the partial sums, they converge almost everywhere back to the function. Same thing, because of this inequality, as repeat the same argument as the density argument for differentiating the integral for the fundamental theorem of calculus. So that's great. So if you want to study Fourier series, it's great to study maximal functions. What about the partial sums? Well, the partial sums are very intriguing because the partial sums, it turns out, do not converge pointwise almost everywhere for integrable functions. In fact, Kolmogorov gave sort of blew everyone's mind when he gave an example of an integrable function whose Fourier series diverges everywhere. So that's pretty weird. Well, it's a little bit explained, it's a tremendous oversimplification. But morally speaking, the nth partial sum of a Fourier series does not look like M, does not look like the maximal function. Does not look like we're taking the function F and averaging it. Rather, it looks like something called the Hilbert transform of F. And Hilbert transform of F, again, you know, great experts, probably the majority of you have seen this thousands of times, know loads about this. Those who haven't dreamed about it all the time, as I keep saying, this is the Hilbert transform. It is called a singular integral because if you think about putting F, the simplest of all functions, let's say the function 1. Let's just put in the function identically 1. That's an L infinity bounded function, the simplest bounded function other than 0 that I know. You get the integral from minus infinity to infinity dy over y. And this is something I would have put down as a calculus student here, I'm sure, on an exam, but unfortunately, that's just not right because, you know, you're supposed to integrate functions that are absolutely integral. You're supposed to be able to take the absolute value, integrate, and get something finite. The theory of integration pertains to that. If you do that here, I mean, the integral from minus infinity to 0 is sort of minus infinity, and then the integral from 0, the positive part of 1 over y, integral from 0 to that's plus infinity, and it's just sort of, anyway. So in a way, this is kind of, it almost looks like nonsense, but you can make sense out of this, in the sense that if you're careful, and you integrate away from the origin, then this will make perfect sense, and you can take the limit as the amount you truncated away converges to 0, it's called the principal value integral, and in fact, this is a very, very nice operator on LP. It's a bounded operator on LP when P is strictly between 1 and infinity, and it turns out, again, not very difficult to see that H is so related to all the different partial sums simultaneously that its boundedness immediately gives the convergence of the partial sums of the Fourier series on LP, in the LP. And this is true for P away from 1 and infinity. And what I want to say to further hit home, again, for those...
Isn't that a very deep theorem was proved about 40 years ago?
Well, I'm sorry, what now?
The convergence...
the pointwise convergence is incredibly deep and difficult. This is in norm. This is in a metric LP. So that's an old Actually, to propaganda, I mean, you know, I'm a Maryland fan. I mean, the person who proved this, of course, as you know, was here, Marcel Rees, very great mathematician. And he essentially proved this, I would say, and found this stuff. But you're quite right, Peter, that, you know, pointwise convergence, whoa, that's very, very combinatorially very complicated, very difficult. Well, in higher dimensions, you know, let's say you don't really care about Fourier series, but you have to care, let's say, about the most basic of all equations from physics, you know, PDE from physics, the Laplace equation, Laplace U equal F. Why the maximal function enters, oh, I'm sorry, again, I think I skipped. I basically want to say, let's see, where is it here? Right. I want to say basically that, well, yeah, H is controlled by M. That's what I want to say. In other words, the Hilbert transform and therefore partial sums of Fourier series, that's also in some sense controlled by maximal functions. Not quite as obvious how. In fact, and this, again, I have some divided loyalties. I mean, Maryland, yes, and also Chicago. And Chicago, Calderon and Zygmunt in the 1950s showed, in a way, how M controls H. And because H is so important, it controls the, norm convergence of Fourier series. I mean, M, again, I think M is very important. Well, but let's say we don't care about, so who cares about Fourier series? Well, let's say we care about complex analysis. Let's look at H and hence M and the role they play there. Well, if you take an analytic function in the upper half plane, which is beautiful, and I won't be, let's say V vanishes in infinity or something like that, and it's C infinity up to the boundary or something, just beautiful. F of Z is U of Z plus IV of Z, and a beautiful function, and we identify a function in the upper half plane with its boundary values on the real line. Then the passage from the real to the imaginary part in the upper half plane, translated to the real line, where we're making this identification of boundary value with function in the upper half plane, is literally, the Hilbert transform, H, is literally the passage from U to V. So identifying functions in the upper half plane with their boundary values on the real line, the Hilbert transform is nothing more or less than the passage from the real to the imaginary part of complex analytic functions. So it's pretty, if you wanted to study complex analytic functions, I think that's pretty important. And M controls H. So, I'm propagandizing and you get it for M. PDE, let's look at that very quickly. Again, now this is an important equation, everybody knows that, Laplacian of U equal F. And we want to solve it. So we start with F, and it isn't the passage from F to U that we want to study, because if you give me F, I don't want to study U, I want to make sure that U has two partial derivatives. Because if it doesn't have any partial derivatives, what am I doing applying a second order operator to it, like Laplacian? So this is the passage that is sort of something I want to study and prove that is a nice operator. And actually, this operator is a convolution operator. In other words, takes this form, and the kernel here plays exactly the role in Rn as 1 over y does in R1 for the Hilbert transform. So even though, of course, it's not literally the Hilbert transform, which is a one-dimensional operator, it's the closest thing in n dimensions you could possibly get to the Hilbert transform. And so it's the same story. I mean, you want to study this operator, F goes to the second partial derivative. You must study it. It's exactly like studying the Hilbert transform, only there's certain magic tricks that you cannot apply. You can apply in one dimension, you can't apply in n dimensions. It's the same story, basically. So M is M controls a lot of things. And here I'm propagandizing for Calderon and Zygmunt. It's not true, unfortunately. You might think, well, maybe it's H controlled by M in this way. No, it isn't, because it's, the pros all have known for many, many years, of course, all of us, that if F is bounded, H of F is probably not bounded. Because, 1 over y integrated is too infinite for that to happen. So you don't have this pointwise majorization. And the control of how M controls H is very interesting and kind of a Calderon-Zygmunt story. And if you haven't seen it, it is something that's very important and interesting. Okay, very good. Now, what I really want to do here, because this is a colloquium. I'm trying to talk about some classical things, but I would like to get to some sort of things that are not 100 years old and so on. And, and M and H have been known for many, many years. In Rn, if you want to study harmonic analysis, for example, but not just harmonic, but let's say, you have to come to grips with much more complicated variants of maximal functions. So what do I mean by that? I mean that instead of averaging a function in Rn over a ball, you might have to average it over, well, a cube is, to be honest, kind of not very different from a ball. The theory is sort of the same, we'll see. But maybe over long, thin ellipsoids, or over rectangles that are long and thin. And it turns out to be very, very different theory. Very much more complicated, and I want to talk a little bit about that. And it's sort of forced on you. It's not like we say, well, I think I don't really like discs anymore, balls, and those are kind of nice. Now let's pass to something, some geometric figure that's sort of more interesting or more complicated, and then you just for the fun of it, you do. It's not like that. I mean, and so what I mean by that is, if you take a function of two variables, which we want to take, and you Fourier analyze it, this is the Fourier, double Fourier series, indexed by two frequencies now instead of one, n1 and n2 are integers. So that, of course, we all know that's what a double Fourier series looks like. We have a multiple Fourier series on the n torus. This is 2 torus, which is bad enough, mystical enough. And then we have, how do you define, if you have a doubly indexed, n1 and n2, a double sum, how do you take the partial sums? They're not well defined. You take the disk partial sums, summing over all frequencies inside a disk of radius r for the frequencies n1 and n2, or you could take square partial sums, for example. Take any partial sum you like. You can define your favorite, but I think it's fair to say that disks and squares are, things that you naturally would be wondering about. And for P, this is very interesting here, in my opinion. And I'm a little biased here, but which I'll get to. If P is kind of amazing, even though for on the circle, one torus, the partial sums of the Fourier series converge to the function in LP when P is strictly between 1 and infinity. So it's a very successful theory. Actually, for every P not equal to 2, this convergence fails on the 2 torus for disk partial sums. So if you feel like some people, I could take a poll, how many of you think that the disk partial sums are the most natural partial sums to consider, or square partial sums? I don't know. I don't know. The disk partial sums fail. They do not converge to the function in norm, in the LP metric, when P and P equal 2, these are just projection operators. So it's very clear that they're uniformly bounded. Projections, when you project the vector, it's just uniformly bounded with norm 1. It's just clear that this is going to work. But when P is different from 2, when it's not clear, immediately obvious by abstract nonsense in Hilbert space theory, it's going to work. It doesn't work. And but it does work on squares, square partial sums. And I want to talk about that. But I do want to, again, I'm trying to propagandize, the last name. But I mean, you notice there is a first name here. And in fact, I remember a seminar here at Professor Grace's house in the evening where Charlie came and talked about this new result and so on, that he had disproven what was called disk conjecture. Disk conjecture, by the way, was that these should converge in the metric LP for a certain range of P. Not for all P between 1 and infinity. It's pretty well known that wasn't going to work, but for a certain range of P. I won't go into it here. And the reason it doesn't work is very interesting. And again, more propaganda. What Charlie realized is that the disk partial sums are again controlled by a maximal function. But the maximal function that they're controlled by takes the supremum of averages, but over the class of all rectangles centered at a point where the rectangles are arbitrary side length and can rotate, can take any kind of orientation that you like. And those operators are unbounded on every P for P less than infinity. They're obviously bounded on infinity. Every maximal, when you average a bounded quantity, it's bounded. That's just abstract nonsense. But other than that, you get no positive result for that maximal operator. So, I would have thought when I was a student here that the fundamental theorem of calculus for Lebesgue should be an abstract nonsense thing in the sense that you're in the plane, you take some figure, you shrink it down, nicely to a point, and then those averages converge to the function. And it's just not true. You take little tiny rectangles, if you don't watch the orientation of them, and their eccentricities, they can be really tiny in diameter, but the ratio of the two sides might be extremely large. The eccentricity could be out of control, and the orientation is out of control by definition in this maximal. It doesn't work. It doesn't work. There are characteristic functions of sets for which it doesn't work. You can't average and converge to the value 1 or 0 almost every. It just doesn't work almost every. So this was quite something. I mean, and another though, as surprising and as beautiful as the whole thing was, another illustration of how maximal functions, and in this case not hardly with respect to balls, hardly little would control interesting and important operators, and in this case in Fourier analysis. So here's it's called Kikeya. There's something called the Kikeya needle problem, which relates to this, and because the rectangle is like a needle, and as it rotates, and so anyway, I'm not going into that right here, but this is the definition. You take the supremum of the averages over every rectangle containing the point, and any rectangle, any orientation, any size. So that's a horrendous operator, not bounded, and therefore the disk conjecture was wrong, and that was Charles. And now, square partial sum operators are controlled by something that I guess I was very obsessed with for a long period of time. I want to talk a little bit about that. And that is the double Hilbert transform. So there in the plane, you convolve with the kernel. It doesn't really look like 1 over y does in R1. And why doesn't it? Because this kernel, as everyone can plainly see, dares to blow up on a higher dimensional set. It doesn't blow up at a stupid point at the origin, like 1 over y does. Or like the Calderon-Zygmunt kernels studying the Laplace operator, which blows up. They're kind of higher dimensional analogs of 1 over y, but they still only blow up at the origin. Here, this blows up on the axes, every point of the coordinate axes, and that is kind of, that's a hint, things are going to be a little harder, a lot harder. And it has a higher dimensional. So one thing that's unknown, that's very interesting, is how do you do singular integrals? How do you take an operator which takes every input function f and convolves with a kernel whose singularity set is higher dimensional? This is still very mysterious, very deep, very interesting. But this is the simplest case, called the product case, because I'm taking 1 over x times 1 tensoring two copies of the Hilbert transform, 1 over x and 1 over y, and that creates the simplest one-dimensional singularities. And already we have a lot of headaches here. Good headaches, though. So the maximal operator that controls this is where I'm averaging the absolute value of the function over all rectangles, but with sides parallel to the axis. So they don't rotate. And that turns out to be bounded on LP, on all LP for P between 1 and infinity, but it's not good on L1. It's probably infinite everywhere on L1. If F is in L1, you do not have good behavior of this so-called strong maximal operator where the rectangles are sides parallel to the axes, but they're two parameter. Their side lengths are arbitrary. Not good. So the sharp result here, again, propagandizing for Chicago, although I'm not going to claim, actually I think Yesin was at Princeton. Marcinkiewicz was at neither. So basically, the sharp result, kind of interesting, is that if f is in L log L, let's say n is 2, just for simplicity, we're in the plane. What is the sharp result? What's the best you can do? When is ms of f finite, for example, for f? And the answer is, if f is in L1, not enough. If f is in L1, ms of f is probably infinite all over the place. But f has to be in L log L. What does that mean? It means that the absolute value of f times the log plus of the absolute value of f has to integrate to something finite. That's what L log L means. It's a little bit stronger than just L1, but weaker than all the LP spaces for P greater than. So, okay, so this is a good maximal operator, but not completely trivial to understand. Yeah, I'm not going to get to that. Okay, let's see, what do we want to say? Yes. Well, let me now turn to, okay, so the point is maximal, so what have I said so far? I've said maximal operators are important, and they're unfortunately or fortunately, there are many of them. So there's Hardy-Littlewood, and we know that's weak 1-1, bound in LP and all this stuff. How do we do that? How do we handle maximal operators? How do we prove them? Well, there's the classical Hardy-Littlewood. I'll show you real quickly if you haven't seen it, how you deal with Hardy-Littlewood. But then what I really want to show, and I certainly hope I have time, at least to sketch or give you a flavor, is there is actually a way to prove new maximal functions being examined and positive theorems proved using old maximal functions. And so that, I think, is of some interest. So you can get new results on harder maximal operators. So we're going to show, for example, how to reduce the two-dimensional strong maximal operator for rectangles to the Hardy-Littlewood operator in one dimension. And the three-dimensional operator will be reduced to the two-dimensional operator. So by induction. And that's going to open up a whole new machine that you're going to see to prove, because an n-dimensional object with n free parameters is controlled by an n-1 parameter parameter animal maximal operator. And that means morally that simpler things are controlling more complicated things. And so what that's going to mean in the biggest picture is that you give me a maximal operator. Well, I would like to tell you, give me any maximal operator at all, no problem. I just put in this machine and there's some simpler operator that I understand that immediately shows me how to do it. No, not at all. But in many cases, this does work. And that's the end of my talk in some sense. But I have a few more minutes, so I'm going to just see, let's see if we can get to a little funny bit, and I don't know how much further I can get. Okay, how do you get the control the Hardy-Littlewood operator? So what you do, it turns out, is you appeal to something which I personally like, and I think I also learned here, by the way, the Vitali covering lemma. So it's a very simple geometric question about balls, well, because we're averaging with respect to balls in Rn, and it says, it asks the following. It dates back to literally 1900 or something like that, or the beginning of the Lebesgue integral, 1900, whatever, very old, last one here. I give you finitely many balls in space. And I want a sub-collection of the balls. This is the question. Can you or can you not select a sub-collection with the following two opposing properties? Okay? Property number one, I want the sub-collection disjoint. So, the original collection of 5 million balls, they have different sizes, they're placed in a messy way all over space, they overlap in the wildest possible way, and I don't like the overlap. So I want a sub-collection which is disjoint. So okay, no problem, just take one of them. By definition, disjoint. Property 2 opposes that, because okay, you take one of them, but what I want is the sub-collection, which has twiddles over it, has to capture at least, in Rn, 3 to the minus n times the volume of the union of the original family of balls. So it's no good to just say take one of them, because you have zillions of them, and just taking one of them does nothing in terms of capturing the spirit of the entire family of balls in this very precise sense. Give me at least 3 to the minus n times the measure of all the balls, original balls, in the subcollection, in this exact sense. And Vitali showed how to do it. We'll go over it very quickly. Most of you remember this. But I claim, given this Vitali covering lemma, I claim that this estimate of the maximal operator, the fundamental one, is completely immediate. It's obvious. So, this looks like a kind of a what do we call it? A Putnam, a kind of a simple, tricky, geometric, very basic thing. But yet, here it is. It implies this immediately, and it's not a silly little thing. It turns out to be a very important thing. So here's a little bit of a sketch of the proof. So I guess, let's see. So we take the set where m of f is big. So what does it mean? I guess for every point in the set, you choose a ball centered at that point, b sub x, centered at x, where the average is big. That's what you mean by the maximal function. I mean, the maximal function is bigger than alpha. What does it mean? It means there's a ball centered at that point where the average is big. Okay, so you take bx. Well, by some, our topologists in the audience can tell us that means, I learned that here too, that there's actually a countable subcollection of these open balls that can be chosen that already covers this set. So in other words, if for each point in the alpha you take a ball, then you've covered all of the alpha by these open balls, and by some point set topology, there's a countable subcollection of these bx's that already do the job of the cover. And now, suppose they were disjoint. They're not. There's no reason why they would be, but suppose they were disjoint. Let's estimate the measure of E alpha. E alpha is contained in the union of these disjoint bk. So the measure is less than or equal to the sum of the measures, because the balls cover E alpha. And they're disjoint. So now each measure of bk of alpha, doing a little tiny first grade arithmetic, because the average over f, the absolute value of f over these balls is bigger than alpha, it means the measure of b alpha is dominated by 1 over alpha times the integral of f over the ball, summing over k. This is what you get. Now, if the balls are disjoint, the sum of the characteristics, well, let's put it this way. If the balls are disjoint and you sum integrals over disjoint sets, that's going to be dominated by the integral over the union of the absolute value of f, dominated by the L1 norm of f, QED. The balls are not disjoint, but the whole point of Vitali's covering lemma is you might as well assume they're disjoint because you get the mess of the million original balls. Well, they're infinitely many, they're countably many, but you just estimate them. If you can estimate the measure of the first n of them independent of n and let n tend to infinity, you can control the union of all of them. So without loss of generality, there are finally many of them, and you pass to a disjoint subcollection, and which captures at least a fixed fraction of the measure of all of them, so you can assume without loss of generality they're disjoint, and so this works. The one additional thing I want to say is that when you sum the characteristic functions in this analysis of the balls that you've chosen, and they're disjoint, and this is a very, very pedantic remark indeed, but it will be important later. The English words, the balls are disjoint, in terms of the sum of their characteristic functions, observe means that that sum is bounded by 1. Not a very deep statement. But this f is in L1, and this sum is bounded by 1, and therefore an L1 function times an L infinity function, that's okay. You can integrate that. We will see when we get to the strong maximal function, or more complicated situations, where f is in L log L, we'll want this function here, well, it cannot be in L infinity, but we'll want it to be in what's called the dual class of L log L, which is actually what's called the exponential class. So we'll get to that. But anyway, this will be important later on. It won't just be disjoint or whatever, bounded and so on. How do you prove the Vitali covering lemma? Well, it's a selection process, and it's a very simple one. And I remember, trying to deal with rectangles, because that's where I'm going. I'm a theorem that I worked on with Vitali many years ago, Cordova. I remember that we didn't realize the importance in the Vitali covering lemma, if you could believe this, I think completely, of the only really major idea in the theorem, in the proof of it, which is to order the balls. So I give you 5 million balls in space, and I say, give me a way of picking out, the sub-collection and so on that Vitali wants. And the proof consists of exactly one idea, which is order the balls so that their radii decrease. That's the proof. Order them. So you start with the biggest ball, and you select the biggest ball first. And then all you do is just shift into automatic gear and do what you have to do, which is, now you get to the second ball on the list. Are you going to take it or not? Well, if it touches the first ball, you better not take it, because you want a disjoint subcollection. So you throw it out. Okay? And you look at the third ball. You're going to take it? Well, does it touch the first ball that you selected? No, it doesn't. You take it. Go down the list and keep taking if and only if that ball is disjoint from what you've already selected, because you want a disjoint subcollection. Okay, now you finish doing that. That works. And why does it work, by the way? One line. It works because it turns out that you claim that all the balls are contained in the threefold enlargement, concentric enlargement of the balls that you actually picked out. And that's why you haven't by definition, you have disjoint balls. But then the second property that you have at least a fixed fraction of the measure is gotten by the fact that if here's a ball that you threw away, then you threw it away because there was a bigger ball, a previous ball on the list that actually dared to intersect it. And then you can convince yourself that if you enlarge this selected ball that's bigger than this little ball, and you enlarge it concentrically by a factor of 3, it will swallow up entirely the little ball. And that's the proof. That proves that the balls that you threw away are contained in the threefold enlargement of what you kept, and so that controls the measure of what you threw away by the measure of what you kept, and that's the end.
Do you need functional choice for the first step?
I'm sorry, what is it now?
Do you need functional choice for the first step?
Axiom of choice is asking.
Oh, axiom of choice. Well, it's a finite set of balls. Finite set of balls. Because if I have an infinite set of balls, and I say, well, wait a minute, now that's not finite. I mean, if you go back to the proof, you reach point, you have a ball that's uncountable, but then whatever you call it from point set topology, second countability, whatever it is, you have a countable collection of balls whose union is E alpha, contains E alpha, covers this set. And now that's infinite, countably infinite. So now what I'm saying is if you can estimate the measure, not of E alpha, but of the first n of those balls, and independent of n, you can let n tend to infinity, and that will estimate the measure of all infinitely many. So in other words, there's a basic fact of measure theory, a Lebesgue measure, that if you have a sequence of nested sets, and the measure of the union is the limit of the measures. And so if you can get control of the measure of each one of those terms and let n tend to infinity, that controls the measure of the union. So you can assume, what I'm babbling here is you can assume there are only finitely many balls in this Vitali cover. So they're finitely many. I don't think there's an axiom. No expert on the axiom. stories of logic, but I think you don't face that. So I think so. No, I don't. One thing I didn't learn here definitely was mathematical logic. Maybe we can talk about that. Maybe Pardon? I chose not to. My brain power limited me to certain courses in a certain direction. I would love to learn it, but so. Oh, anyway, so theorem of Jessen-Martin, Zygmunt. Again, depending on, see, it's interesting because the Hardy-Littlewood result doesn't really depend on n, if you think about it. What do I mean by that? I mean we're doing n-dimensional Fourier analysis. We're working with the n-dimensional maximal function. We're working with n-dimensional balls. But where is n in that? I say that the maximal operator for balls on Rn is bounded on LP, P strictly between 1 and infinity. There's no n there particularly. You know, you're in Rn, but who cares? And then it's weak type, what's called weak type, 1, 1. That means if F is in L1, then there's something. Well, L1 is there's no n in 1. L1 of Rn. So in other words, you don't pay much attention to the fact that you're in Rn. Ball's in Rn. And the Vitali covering lemma said if you have a bigger ball in Rn touching a smaller ball, you take the concentric triple of the bigger ball, it swallows up the small. Well, that's metrics. I mean, that's just metric space abstract nonsense, a triangle inequality that is responsible for that. Nothing to do with n. Dimension. Here, in Jessen-Marcinkiewicz, the minute you have a product situation where, you know, when you have a rectangle, you know, it's a Cartesian product story, so you have n things, n one dimensions that your product, taking a product of, you have rectangles with sides parallel to the axes, and you're souping over averages of the absolute value of f there. So there, I put an n there to remind us this is the n-dimensional strong maximal function, Rn. Here, the very class of functions that you deal with depends fundamentally on n. That's very interesting. So it's not L1. The space is all functions, again I remind you, such as the absolute value of a function times the log plus of the absolute value of a function to the n minus first power. There's a dimension coming in. On the unit cube in Rn is finite when you integrate. So it's fundamental. It's a very much deeper kind of thing in the sense that it depends on n. This theory will really be a true n-dimensional theory. In some sense, the Calderon-Zygmunt theory, in a way, is one-dimensional in the sense that it doesn't really take into account much. It's the dilations that count. In other words, you have a ball, or you have some figure, and you have a one-parameter family of stretchings, of dilations. Here, you take, it doesn't matter about, it's nothing to do with rectangles or whatever. Take any blob, amoeba-shaped blob, and take a two-parameter family of dilations where in the x and y direction, you dilate the amoeba-shaped blob independently. So that is the strong, it doesn't have to be rectangles, that's the strong. So it's a theory of taking products, Cartesian products, and the 2, or the n, is how many factor spaces you have. And the theory depends fundamentally on how many factor spaces. And the proof of Jessen-Marcinkiewicz and Zygmunt, and I'm a little short on time here, so I'm going to go, I'm sorry, I apologize. I'm going to go a little quickly here, is to point-wise dominate. Let's take n equal 2, that shows us. In 2 dimensions, I'm going to average over this rectangle. I'm going to call the rectangle I cross J, where I and J are intervals. And what they observe is something very, very simple, and it proves it. They dominated the strong maximal function in 2 dimensions of f, point-wise directly, with constant 1 I might have. Shows you how simple and basic here, but it's a ingenious but simple. A composition of 2 one-dimensional maximal operators. And since we understand one-dimensional operators, maximal operators, we understand the 2-dimensional operator. And let me just say in English why that's true. You want to average over a rectangle. Okay. By Fubini's theorem, I think everybody can convince themselves instantly that if I want to average, what I do is I draw, here's the point x I'm talking about. I draw a horizontal segment through x, and for every point on this horizontal segment, I construct a vertical segment, like this, parallel to j, through this point. I average the function on this vertical segment, and then I slide the point over this horizontal segment parallel to I. The average over this horizontal segment of these averages, by Fubini's theorem, is the average over the rectangle. That is their fundamental observation. If you translate that into maximal function language, it simply says that at the point x, the 2-dimensional strong maximal function of f at x, taking a soup over all the possible rectangles, would be dominated by m of x1, I guess I'm in the wrong word, I don't, it doesn't matter, m of x1 of m of x2 of f. And we had known the behavior of one-dimensional maximal operators very well since Hardy-Littlewood, and so you can believe me, if you compose two well-known one-dimensional operators, you get a domination from the two-dimensional strong thing, and you know that's the S and Martin sigma. And by the way, why aren't we good? If I dare to put in an F in L1, I say, come on, F. This should be weak 1, 1, 2. I should be able to put in an N. If this is a decent maximal operator, I put in an L1 function F, and out should come MF, a nice maximal function. And I say no, and why not? You can see very clearly already from this proof. If F is in L1, the first maximal operator will not map you to L1. M is not bounded on L1. So M of F is okay, but it's no longer in L1. It's what's called in weak L1. And now you can't even integrate that function. And you can't even define a maximal operator of a function that's not integrable. Because you can't average. You can't integrate over it and divide. I mean, that's an average involves integration. So what I'm saying is you can't, this shows you very clearly, since you have two maximal operators cooperating with each other, the first one will like the L1 function, but the second one will reject M of the first one. So you can already see why M2, two-dimensional thing, is no good on L1. And now, what I want to say, okay, what I want to do, do I have like 2 more minutes? No. Okay, so what I want to do is to show you that you can actually directly prove the sharp covering lemma in n dimensions, which recaptures the S in Marcinkiewicz-Zygmunt theorem. And that means the following. I give you finitely many rectangles in Rn, in R little n, and so capital N is the number of rectangles. We don't really, they're going to let that go to infinity anyway, so technically we have finitely many rectangles. I want a subcollection doing the two things that Vitali wanted. Well, I want to capture at least a fixed fraction. The twiddles are the ones I select. They have to capture a fixed fraction of the original family. And what is this nonsense? I can't get disjoints. I can't get rectangles that are disjoint. Not that I'm too stupid to do it. You can prove you can't do it. If you could get disjoint rectangles, you would have a weak 1-1 result. You'd be able to have a theory, nice theory on L, which you know you don't have. The correct theory is L log L. Functions in L log L are the ones for which you have a right to take a two-dimensional strong maximal function, MS. This is the right estimate. To say disjoint would mean I put an L infinity here. I would say the sum of characteristic functions of disjoint sets is bounded. I can't do that. I have to, so what I'm saying, I'm sorry, I'm getting, it's very fast, and it's getting even less apparent what I mean than before. What I'm trying to babble here is that this is morally the same as Vitali, and what I'm saying here is I want disjoint, I want to capture a fixed fraction of the measure of the original rectangles, and I want almost disjointness. What does that mean? I want sparseness. That means the measure of the set of points that are in loads of these rectangles, where there's loads of overlap, is very small. And that's true here. I mean, if you can exponentiate a function and integrate it and get something finite, you better not have a lot of points where the function you're exponentiating is large. Right? If e to the f is a positive function, e to the f integrated over the unit square is finite, and I ask, well, how many points, what's the measure of the set of points where f is large? It better be very, very small. Because I'm taking, you know, when you take e, this is another one I learned here, e to a big number is very, very big. So, almost done. So, this is what we get. And the proof of the covering lemma, well, you start, okay, and here's, again, Fefferman and I took us, this is one of those things where after you realize it, you kill yourself for not having realized it's so trivial. You pay attention to the ordering in Vitali, and what you do is you cannot order, let's go to 2 dimensions. You cannot order the rectangles in terms of their size. You've got 2 sizes, you've got 2 lengths, and how do you order, what's the biggest rectangle? Area won't work, that's not a criterion that works at all. So you choose one, doesn't matter which one, you choose the one of the parameters and you order that. So let's take the vertical parameter. You order the rectangles in terms of decreasing vertical size. And so what happened in the Vitali case Well, you took the only parameter you had and ordered in that. Here you have two parameters you take. Okay, so now you choose the first one, and now what is the selection procedure? The selection procedure turns out to be that you go down the list and you take a given rectangle if and only if the part of that rectangle, I'd like to say you only take it as disjoint from what you already, but that doesn't work. We know it doesn't. So what you do is you take it if and only if the stuff you selected before occupies more than, let's say, less than, let's say, half of the measure of that given rectangle. So morally, although that rectangle is not disjoint from what you've already taken, it's morally disjoint. Half of its mass, half of its area, is not in what you've already taken. It's half free of what. So that's the selection criteria that replaces. And now, let me just say, because I am running out of time, who cares about anything? I mean, what good does this do? Well, it turns out to be, believe it or not, important. If this is a picture of a rectangle that you threw away, then it turns out that when you slice that rectangle, so what does it mean that you threw away this rectangle? It means that the measure of all the preceding rectangles that invade into this rectangle occupies at least half the measure of that rectangle. That's why you threw it away, because morally, the stuff you selected before got into it too much. And now, because of the order, which is the crucial, and I'm making everything dyadic, so these things pass all the way through, they don't just stop halfway through. But it's okay if they don't worry about it. And you slice the picture to go to one dimension, the same statement is true. The same statement is true. And that's why ordering was so important, that the stuff that came before it was longer in the vertical direction, so when you slice in the opposite, in the horizontal direction, the intervals here, one-dimensional intervals, have to invade at least half of the measure of that rectangle. It turned out that that allowed us to control a two-dimensional situation with a one-dimension, passed directly by induction down one dimension. And I don't have, well, you can see what's happening. I'm literally going to flying in different directions here but as I end. But I think what I'm going to do here is just pass to what you can do with this, because I think the key question for even experts at this point who haven't seen this, or non-experts, is this top thing? Who cares? Because the essay Marcinkiewicz-Ziegenmann strong maximal theory was known for decades and decades. Who would care about this? And let me just give you a few little answers, and then I will shut up. So a few things you can do with this method of using convergence and controlling harder maximal operators, in this case n parameter, n dimensional by n minus 1 directly by this slice. Suppose the Lord gives you, instead of Lebesgue measure, says to you, I no longer approve of Lebesgue measure, and I do not want you to mention it anymore. I like the measure mu, a particular mu. So now we form the maximal operator. And the maximal operator, the strong maximal operator, or any maximal operator, we'll call it mu, although we really shouldn't have to, because we've been directed to use mu only and talk only about that. So the absolute value of f, of course, is integrated with respect to this measure, and so we have our strong maximal operator, but not with respect to Lebesgue measure. If mu is a product measure of two measures that are one-dimensional, it turns out the S in Marcinkiewicz-Ziegenmann method works perfectly well. You recover the whole theory, everything, everyone's happy and go away. If mu is not a product measure, there is nothing to do. Well, our method works. Same method works. Not for any mu. It turns out, for those who are pros and know this, there are the classical weight classes called the Muckenhouse weight classes, the AP classes. And it turns out that if your mu belongs uniformly to a Muckenhouse class, a weight class, then you recover the field. And again, if mu is not a product measure with the usual proof, it's very simple, Fubini's theorem, this and that, you can just see immediately there's nothing you can do. So that's one thing. But there are many others, there's several other things. I just want to propagandize for that, and again, I will shut up. Okay, if you take rectangles, and there are reasons for this, which I won't get into, but having to do with harmonic analysis and other things. If you take, instead of rectangles with sides parallel to the axes, Charlie showed if you can use the Kakea maximal operator where the rectangles are allowed to tilt arbitrarily. That's a horrible theory in the sense that it's unbounded on every finite LP space, the Kakea maximal operator. But what happens if you restrict the orientations to a sequence of directions. And the most simple one you could hope would be okay would be a sequence of directions that morally is only one direction. That is a sequence of directions that converge extremely rapidly to one fixed direction. Like 2 to the minus, let's say theta I, the angle theta I that you make with one fixed preferred direction, let's say horizontal, is 2 to the minus I. And that's called a lacunary situation. You take the supremum of over all rectangles, arbitrary side lengths, but allowed only to orient themselves in one of these very rapidly converging directions to a fixed direction. It turns out that that operator, the first estimates for that it's a good operator, it's bound on all LP, P between 1 and infinity, the first estimates by this method of coverage lines. And by the way, it was MS, the strong maximal operator, that controlled M theta. So there's this hierarchy of maximal operators. The 28th dimensional strong maximal operator controlled by the 27th. Here, this this lacunary direction maximal operator controlled by the 2-dimensional strong maximal. So that's that. And then that was originally proven by Stromberg using our method, and then Cordoba and myself extended it to L2, and then Eli Stein and company used totally different methods, very powerful methods to control, get LP estimates. And I might add, open problem, what's the best result near L1? L log L to the 1. And that, I think, my humble opinion, covering lemmas would play well. They tend to be a little bit better near L1. In particular, Antony Zygmunt, if anyone knew him here, and I think many did, had a way of sort of smiling with a twinkle in his eye and posing a conjecture that was incredibly impossible, that you just couldn't even hope to answer. And one of them, the Zygmunt conjecture, I remember as a graduate student, Stein talking about it, and who knew how to do it. What about the following? Take in R3 the following class of rectangles. The side lengths of the rectangles are S by T by S times T, let's say. So it's a 2-parameter family. S and T are the 2 independent parameters. The third side length is given as a function of the first 2. So there are only really 2 free parameters, S and T. But this takes place in R3. But who cares whether it takes place in R50 or in R100? There are 2 parameters, S and T. It should be the parameters that are important, as it was the number of factors, not the ambient space R3, who cares about that? So this should act like the 2-dimensional strong maximal operator in R2, where the number of parameters is equal to the dimension of the ambient space. Well, it turned out Antonio Cordoba, using this method, covering lemmas, was able to settle it. So that was really, and it's a very, very beautiful argument. I really recommend it. Very, very lovely. And then finally, the last one, and maybe most important, is the following. That there may be a number of ways you can handle maximal operators. But I claim that understanding the geometry of the sets is very important. Why is that? Because it turns out that let me put it like this. If you want to estimate an integral of a function, and you have a bunch of disjoint balls, you have a bunch of disjoint balls, and you want to integrate over the union of them, well, that's just the sum of the individual integrals over the disjoint balls. Well, when you get to more complicated sets, they won't be disjoint anymore. But if you don't understand the geometry of how to deal with these sets, you can't do analysis with respect to these sets. In other words, you literally, when you do singular integral theory, there's a whole singular integral theory behind, like, generalizing the double Hilbert transform. I haven't talked about that at all. If you want to attack that, there's something called Journet was a very brilliant mathematician in this area, and came up with a relative of the covering lemma I just talked about. Not the same at all. Very, very interesting, very different, very brilliant, but related. And a covering lemma kind of thing. And if you don't understand the geometry of the sets, you can't do any of the analysis. You can't handle the singular integrals, can't do anything. So it's not just, if I just come up to you, I mean, if a good fairy comes up to you and says, these maximal operators are bounded, don't worry about it. I guarantee they are. That's not enough. You have to understand the geometry of the sets involved, and not just the boundedness of the operator. So that's another strength of this method. I mean, I'm propagandizing for my own method here, but I mean, that's why you just need that covering lemma kind of thing. Very important. And then finally, an open problem, I would say, is singular integrals in higher dimensional singularity sets. Singular integrals that are invariant under other groups of dilation have been studied by Ricci and Stein. The really deep maximal functions and the really deep theory near L1 still totally mystical. So this area is completely wide open